In 2007, Intel, the most powerful semiconductor manufacturer on Earth, agreed to pay a penalty of $250 million. The entity receiving this massive payout did not manufacture a single physical product. By all traditional metrics of the hardware industry, they were already dead. But this specific court docket, Transmeta Corporation versus Intel, secured a multi-million-dollar extraction from an entrenched monopoly. This settlement was the final activation of a strategic trap built into the company's patent portfolio years before the first courtroom filing. In 1995, a company named Transmeta incorporated in Silicon Valley. For nearly 5 years, they maintained a completely blank web page and enforced over 2,000 non-disclosure agreements. Linus Torvalds, the creator of the Linux kernel and the architect of the world's most critical open-source software, stepped away from the public eye to work inside this windowless building. The tech press speculated wildly. Theories ranged from a processor capable of executing x86 code at impossible speeds, to rumors that the company was reverse engineering alien technology. The engineering reality was stranger. Transmeta was attempting to bypass the physical, thermodynamic limits of silicon computing by building a complex digital hallucination. Transmeta did not actually build an x86 processor. They built a VLIW engine, a very long instruction word architecture that was explicitly designed to mimic one. Standard x86 instructions arrive in chaotic links, like a mismatched freight train. VLIW instructions are perfectly uniform, executing simultaneously like standard shipping containers. To bridge this gap, Transmeta's code morphing software translated and repacked those chaotic x86 instructions into native VLIW molecules on the fly. This invisible abstraction layer was highly effective. It successfully booted standard desktop operating systems directly at the silicon level. The software and the user never knew they were running on emulated hardware. By replacing billions of physical logic gates with software instructions, Transmeta drastically reduced the thermal output of the chip. But this abstraction introduced a strict, inescapable latency penalty. The core vulnerability of dynamic binary translation is branch misprediction. If the software guesses the wrong instruction path, it triggers an x86 architectural exception. To survive an exception without crashing the operating system, the processor had to instantly reverse time to the exact microsecond before the error occurred. Transmeta achieved this through a highly strict hardware failsafe, utilizing specialized shadow registers and a gated store buffer. This buffer actively quarantined all uncommitted memory writes. Only when a translated instruction trace completed without a single fault would the physical airlock open and commit the data to system memory. If an error was detected, the uncommitted data was violently flushed and the system rolled back to the secure shadow registers. This constant cycle of commit and rollback guaranteed system stability, but the time required to execute it severely crippled the processor's speed for desktop consumers. While consumer laptops demanded raw speed, the early 2000s saw the rise of massive server farms where thermal density became a critical vulnerability. As data centers packed hardware closer together, managing the sheer heat output became an engineering crisis. This chart illustrates Transmeta's underlying algorithm, long-run dynamic voltage scaling. As the software workload decreases, the algorithm dynamically throttles the processor's operational voltage down in precise steps, matching power draw strictly to real-time demand. An architecture that was too sluggish for a premium consumer laptop suddenly offered the only thermal footprint cold enough to sustain densely packed digital grids. Despite its thermal advantages, Transmeta's physical architectures, the Crusoe and the Efficient, could not overcome the raw computational power and immense manufacturing scale of the established x86 monopoly. Facing the collapse of their physical hardware business, the company abandoned silicon manufacturing entirely and weaponized their intellectual property. They had methodically patented the exact algorithms and granular methodologies of long-run power throttling, laying a legal minefield for the rest of the industry. As power consumption limits hit an absolute ceiling, Intel was forced into a massive architectural pivot. They abandoned their power-hungry designs in favor of the highly efficient Pentium M architecture, utilizing the exact power throttling concepts Transmeta had mapped out. Intel eventually paid $250 million to license the very power management philosophy that saved their mobile division from thermal collapse. Today, the dynamic voltage scaling patents generated by this failed hardware project operate beneath the surface of nearly every modern smartphone, laptop, and cloud computing grid. The physical processors themselves are historical artifacts, rotting inside abandoned terminals. Their commercial failure is an undeniable reality of semiconductor economics. Transmeta demonstrated that software could effectively rewrite the thermodynamic constraints of silicon, bypassing traditional bottlenecks of material science. Modern systems now treat physical transistors and the code managing their power as a single integrated mechanism. The boundary between software and silicon has been erased.